Good morning to one and all. Myself R.SRIVEL, working as assistant professor in Sri Shanmugha College of Engineering. So in this I'm going to give a small introduction about microwave amplifiers. So first we are going to discuss about that what is that need for that RF as well as microwave amplifiers. That in most RF and microwave amplifiers today are used with the help of transistor devices such as silicon, germanium, BJTs, gallium arsenide, and heterojunction bipolar transistor, or by using gallium arsenide or indium phosphide FET or gallium arsenide HEMT, that is high electron mobility transistor. Microwave transistor amplifiers are rugged, low cost, reliable, and can be easily integrated in both hybrid and monolithic integrated circuits. So this is a general block diagram of an amplifier block. So in this we have an input voltage source Vs, so and then the input impedance, this is ZS, and then input matching network, and then amplifier that can be designed with an active component, it is a transistor, then output matching network, then a DC bias. So in unit 1 we have discussed about that three consideration. So one is input matching network, stability, as well as bias. So the three step is the important part for an amplifier. So then we have an output matching network, then we have a resistance, output impedance, that is ZL, then it is an input impedance, that is input matching network. So normally we have a low sinusoidal input, that is a small signal, so then we will have an amplified output, that is a linear output voltage that is present at that output side. So that is shown in the figure. So amplifier can be categorized into two manners. So one is according to that input signal. So we have either we have a small signal or we will have a large signal. According to DC biasing scheme of the active component, the transistor can be of either it can be of class A, that is class B, class AB, and class C. There is also another classes such as class D, that is used for digital, and class C and class F. So these all uses the transistor or FET as a switch. So here the transistor can be used as a switch. So from this block diagram, so we will form a equation. Voltage relation of an amplifier can be modeled as, that is output voltage, that is V0 of t, that is equal to A1 into Vi of t plus A2 into Vi the whole square plus A3 into Vi the whole cube into 3 plus HOT. So for a large signal, so normally we will apply a nonlinear input, that is an A1 into Vi of t plus A2 into Vi square of t plus A3 into Vi square of t. So in a nonlinear as an input signal, so we will get a nonlinear sinusoidal output as an output waveform. For a small signal, we are going to apply, that is output voltage, that is approximately that is equal to A1 into Vi of t. So normally we will have a low sinusoidal input, so that can be amplified with the help of an active component. So we will have a sinusoidal output as a waveform. All the amplifiers are inherently non-linear, that is given in the equation. So that is previously we have discussed. However, when the input signal is a small signal, the input and output relationship of an amplifier is approximately linear. So that is output voltage, that is V0 of t, that is approximately equal to A1 into Vi of t. So this is a linear relation. So Vi of t, that should be less than or equal to 2.6 millivolt. This linear relationship applies also to the current as well as to the power. An amplifier that fulfills this condition, first, that is a small signal operation. Second, it is linear, is called a small signal amplifier. So in a small signal amplifier, it contains BJT or FET. This component can be replaced by respective small signal model. For instance, the hybrid PI model can be used for BJT. That is here, that is shown here. So instead of this, we can replace with the help of an hybrid PI model for BJTs as well as for FET, when the input is a small signal. So if we have a small signal, then we have to use an hybrid PI model for BJTs for analysis. So next, so is a general block diagram that is given for an RF amplifier schematic. So in this we have an input signal. So this is an input matching network. So that's the yellow color will represent the matching network. So this is a matching network. So here, so this is an output matching network. It's an input matching network. So this is an input impedance ZS. So this is an output impedance ZL. It is given here. So this is an amplifier circuit. It is given either it can be of class A, class B, class AB. So that we can use based upon that circuit. So based upon application, we can use any type of an class A, class B, class AB, or class C or class D type of an amplifier here. So DC supply that is based upon that gain. So to determine the performance of an amplifier, the following characteristics can be observed. One is, so for a small signal amplifier, the important characteristics are power gain, bandwidth, and noise and phase response. For a large signal, gain compression, dynamic range, harmonic distortion, intermodulation distortion, third order intercept point TOI, that is related to the linearity. For amplifier functioning at RF and microwave frequency, usually of interest is the input and output power relation. So what's the power gain? So power gain is called as the ratio of output power over the input power is called as the power gain. It is usually expressed in dB. So power gain, that is G is equal to 10 log to the base 10 output power divided by input power in dB. So there are number of definitions for power as well as we see shortly. Further, G is a function of frequency and the input signal level. So what's a normally power? Power is equal to V into I. So power gain is preferred for high frequency amplifier as the impedance that is encountered it is, and usually it is a low because that is due to parasitic capacitance. Normally for high frequency, so we will consider the parasitic capacitance. So that capacitance, so we'll have a reactance with respect to the frequency. So it will affect the power. So power will be usually low when we consider the parasitic capacitance. For instance, if the amplifier is required to drive a 50 ohms load, the voltage across the load may be small, although the corresponding current may be large. There is a current gain. For amplifier functioning at low frequency, such as intermediate frequency, it is the voltage gain that is of interest, and such impedance encountered is usually high, that is less parasitic capacitance in this part. For instance, if the output of the IF amplifier drives the demodulator circuit, which is used for digital systems, the impedance looking into digital system is high and large voltage can be developed across this. So in this part, the voltage gain is more convenient. So why power gain for RF and microwave circuits? So by working with the power gain, the RF designer is free from the constraint of system impedance. For instance, in the simple receiver, the block diagram is given below. Each block contributes to some power gain. A large voltage gain can be obtained from the output of final block by attaching a high impedance load here to the output. So first we have RF signal part. So you will have a band pass filter. Then we will have a low noise amplifier. So then we have to get from that we are going to get an intermediate frequency. So for that we are going to use a local oscillator. Then we have a band pass filter. Then again we are going to amplify with that IF intermediate frequency amplifier. Then we are going to connect to an output impedance that is 400 ohms. So that power level P average that is equal to V square divided by 2R. Next, harmonic distortion. When the input signal driving signal is small, the amplifier is linear. So here it is a small signal, so that output will be linear. Harmonic components are almost non-exist here. Harmonics generation reduces the gain of the amplifier as some of the output power fundamental frequency is shifted to higher harmonic. This results in gain compression, that we had discussed earlier. When the input driving signal is too large, the amplifier becomes non-linear. So harmonics are induced at that output for a large signal. So you will get a non-linear output here. So power gain versus frequency for a small signal amplifier. So this is for a large signal. So power components in an amplifier. So just we are going to modify into a 2-port network this amplifier circuit. That is given below here. This is a source network, this is a load network. So it's a reflection coefficient gamma s, gamma 1, then gamma load reflection coefficient. So this is a reflection coefficient, that is gamma 2. So in a 2-port network we have S11, S12, S21, S22. So these things are taken as a source network. So this is an amplifier part, this is an output part. So 2-port power gain. So we have an V1 incident voltage and then reflection voltage V1 plus, V1 minus, V2 plus, V2 minus. So here we have an reflection load impedance, output reflection coefficient, so input reflection, source reflection coefficient. So we have. So from the power component, there are 3 types of power gain can be defined. One is power gain GP, power delivered to the load, divided by input power to the amplifier, that is PL divided by Pin. Next, available power gain GA, that is available load power divided by available input power, PA0 divided by PAS. Transducer gain GT, power delivered to load, available input power, PL divided by PAS. So GP, GA, that is power gain, available power gain, transducer gain can be expressed as a S parameter of the amplifier and the reflection coefficient of the source and load networks. So here it is a power gain. So power gain, that is equal to the ratio of power dissipated in the load ZL to the power delivered to the input of the 2-port network. This gain is independent of ZS, although some active circuits are strongly dependent on ZS. So power delivered to the load, that is ZL, this to the power delivered to the input of 2-port network. So here, so this ratio is called as the power gain GP. Then available gain, the ratio of power available from 2-port network to the available power from the source. This assumes the conjugate matching in both source and the load depends on ZS but not on ZL. Then transducer power gain, that is GT, that is equal to, is the ratio of power delivered to the load to the power available from the source. This depends on both ZS and ZL. If the input and output are conjugately matched to the 2-port network, then the gain is maximized. So from the definition of S parameters, so we have, that is V1 minus, that is equal to S11 into V1 plus. So plus minus will represent that, plus represent the incident, and then minus will represent the reflection. So S11 V1 plus S12 V2 plus, that is equal to S11 into V1 plus S12 into reflection coefficient, lower reflection coefficient into V2 minus. So V2 minus, that is equal to S21 into V1 plus S22 into V2 plus, that is equal to S21 into V1 plus S22 into gamma L into V2 minus. So by eliminating that V2 minus from this equation 3.1a, so this will be eliminated. So then we will have S11, S21 reflection coefficient L divided by 1 minus S22 into reflection coefficient L. So this can be simplified as Zn minus Z0 divided by Zn plus Z0. So this is an input reflection coefficient. Then output reflection coefficient, that is equal to same as this part. So Z out minus Z0 divided by Z out plus Z0.